Good afternoon. Welcome to Science at the Local. My name is Kevin Joseph. I'm one of the coordinators of Science at the Local. Welcome on a very warm Sunday afternoon in the Blue Mountains and in much of New South Wales. Science at the Local takes place in the land of the Darug and the Gundagar, so we'd like to pay respects to Aboriginal people, past, present, and for leaders that are emerging. I am on my own today. Hamish is off being a great dad and family man, so he has his hands full. With me today is Dr. Jessica Veliscek-Carolan. Hopefully I got that right, Jessica. She's a nuclear chemist at ANSTO, and she'll be talking about the future of nuclear waste. Without wasting any time, I'm going to throw it to Jessica. Just to remind everyone, please type your questions into the Q&A section at the bottom of your screen, and then Jessica will happily answer those at the end of her presentation. Over to you, Jessica.
Thanks, Kevin. And yeah, welcome everyone. Thank you for tuning in on this very hot day. I am coming to you from Marrickville in Sydney, so this is Gadigal land, and I'd also like to pay my respects to elders past, present, and emerging. So today I'm going to be talking to you about the future of nuclear waste, reduce, reuse, and recycle. I think I'll just get straight into it. So the first thing I wanted to do was just give a little bit of an introduction to ANSTO for those of you who don't know much about ANSTO. So ANSTO is Australia's nuclear science and technology organisation, and we have Australia's only nuclear reactor, which is a research reactor, not a power reactor. So this is a picture of our research reactor, which is called OPAL. It stands for Open Pool Australian Light Water Reactor. So open pool for obvious reasons. And you can see the beautiful blue Cherenkov glow coming out because it has got that open pool at the top. So the main purpose of the OPAL reactor is to produce medical radioisotopes, which are used for diagnosis and treatment of various diseases. It's also used to irradiate silicon, which is used to make microelectronics, and for scientific research. So the main thing that our reactor does in terms of scientific research is it makes neutrons. So as part of the fission process, there are a lot of neutrons that get generated in the reactor, and those get channeled down beam lines into neutron scattering instruments that are used to understand the structure and the function of what's going on inside lots of different types of materials. As well as our neutron scattering instruments, we also have lots of other research infrastructure. So that includes the Australian synchrotron, which is in Melbourne rather than Sydney, where the OPAL reactor is. And the synchrotron is, I guess, kind of similar to the neutron scattering instruments in that it's also looks at the insides of materials and understands their structure and function, but it uses X-rays to do that rather than neutrons. We also have some particle accelerators at ANSTO at the Lucas Heights campus in Sydney, which are used to for all kinds of applications from environmental to health to understanding radiation damage. And we have 3 research themes, which are human health, the environment, and nuclear fuel cycle. So I work in the nuclear fuel cycle research theme as a chemistry researcher, as Kevin said. And I'm going to talk to you today a little bit about my research and a background into what is the nuclear fuel cycle. So this is a nice little schematic of the nuclear fuel cycle. We start at the front end with uranium and pulling it out of the ground and enriching it to make nuclear fuel. And that nuclear fuel then gets used in nuclear reactors, be they power reactors or research reactors, to make electricity in the case of power reactors, or to make neutrons, or medical isotopes in the case of a research reactor. And then the fuel, after it can no longer sustain a chain reaction, is, I've called it here spent fuel, but we can also refer to that as used fuel or nuclear waste. They're all kind of interchangeable terms for the same thing. Nuclear waste obviously suggests that it's just a waste product and it can't be used anymore. Spent fuel is a kind of in the middle, saying says spent, it still suggests that it's kind of not useful anymore. Whereas used fuel is the term that I tend to use most because it has been used once, but that doesn't mean that we can't still get use or value out of that used fuel. So there are two options then for once the fuel has been through a reactor once. It can either go to be stored and eventually disposed, or we can reprocess the spent fuel and recover the actinide elements like uranium and turn those back into nuclear fuel and go round and round in a circle. So we refer to the open fuel cycle as being the once through cycle, where we go from uranium through to spent fuel storage and disposal, and the closed nuclear fuel cycle when we go round and round in a circle, and it's a closed loop. So there are advantages and disadvantages to both the open and the closed nuclear fuel cycles, but I'm going to be talking mostly about the closed nuclear fuel cycle and talking about the advantages of that, because that's the area of research that I work in. So what are the elements that we want to recover from used nuclear fuel if we're going to close that nuclear fuel cycle and close the loop? So this is a periodic table of elements. I'm guessing most of you are familiar with it, and it contains every element that exists in the universe that we know of. And all of the elements from zinc, which is just here, all the way up to the lanthanides, which start here and end all the way down here. All of those are present in spent or used nuclear fuel because they're fission products that occur due to the fission that happens during fuel being burnt in a nuclear reactor. So the ones that we're particularly interested in today are these actinide elements. So the actinide elements are all the radioactive elements. They're down here at the bottom of the periodic table. Some of them you'd be familiar with, things like uranium, thorium, plutonium, and there's a couple that I'm going to be talking about today that you might be less familiar with, which are these ones in purple that are referred to as the minor actinides. So they're called neptunium, americium, and curium. And they're called minor actinides because there's less of them present in terms of a volume amount in spent nuclear fuel. And the other kind of class of elements that I'm going to be talking about a lot today are the lanthanide elements, which are just here in the periodic table, just above the actinides. And these are fission products that are present in used nuclear fuel, and they're particularly important for minor actinide-lanthanide separation, which I'm going to talk about a bit more later. So what are the benefits of doing this separation and recycling and closing the loop of the nuclear fuel cycle? Well, you can see from this picture that the large majority of what is in used nuclear fuel is still uranium. 94 to 96% of used nuclear fuel is still uranium. So there is, of course, the potential to recover that uranium, recycle it, make it into fuel again, and reuse it. So that would have the benefit of dramatically decreasing the volume of waste that was left over that actually needed to be stored and disposed of in the long term. As well as reducing the volume, the benefits of doing this recycling, separation and recycling is that we could also decrease the radiotoxicity and the lifetime of the waste that needs to be stored and disposed. So if we could completely remove all of the uranium, the plutonium, and those three minor actinides from used nuclear fuel, then that would decrease the lifetime of the waste that required storage and disposal from 130,000 years down to just 270 years. So that's if we only had the fission products remaining. And when we talk about the lifetime, this dotted line is the radiotoxicity level of naturally occurring uranium. So even though there may be some radiotoxicity there still after 270 years, it's equivalent to naturally occurring uranium that just exists in the ground anyway. So this means that if we did this kind of processing of nuclear waste, not only would we be making more complete use of the uranium and the other actinides, so getting more bang for our buck, so to speak, but we also end up with waste that's less hazardous, both to the environment and to people, in terms of volume, toxicity, and lifetime. So reprocessing of use nuclear fuel is something that already happens internationally on a commercial and industrial scale. So that's done using this process, which is called PUREX, which stands for plutonium and uranium extraction. It's a very imaginative title, as many of them are. And basically, this is a process called solvent extraction, where the used nuclear fuel is dissolved in nitric acid. And that's shown, or being shown here as the yellow liquid, which has all of these different shapes in it, which are all the different elements which are in used nuclear fuel. And then you contact that dissolved used fuel with an organic solvent that contains an extractant molecule, which is being represented by these little moons. And basically you mix those together, which is something like mixing your vinegar and oil together when you're making salad dressing. So when you add them initially, they don't want to mix, right? So you have to give it a good shake in order for them to actually contact with each other. And then if you leave it for a while, the two phases separate out again. So that's what happens when you mix an aqueous solvent like the nitric acid and an organic solvent like kerosene is used in this case. You need to shake them up to get them to mix, and then they settle back out into the aqueous phase, which now, the organic phase now contains still that extractant molecule, but it's extracted this star element, which in this case represents uranium and plutonium. And all the other fission products and the minor actinides are still in the aqueous phase in the nitric acid in the yellow down here. So that's how we achieve a separation by solvent extraction or liquid-liquid extraction. So in the PUREX process, the organic molecule that's the extractant, these little moons, is this molecule down here, which is called tributyl phosphate. And it's a really good ligand because it's simple, relatively simple, it's easy and cheap to make. So once we've extracted the uranium and the plutonium using a PUREX process, then you strip the uranium and the plutonium back out of the organic phase and you can convert them into what's called a mixed oxide or MOX fuel. Mixed oxide because it's a mixture of both uranium dioxide and plutonium dioxide, whereas traditional nuclear fuel is just pure uranium dioxide. So this is, in this way, by making MOX fuel out of what was waste, we can get more energy out of the material that otherwise was just going to be disposed for hundreds of thousands of years. So that would increase the number of years that nuclear power would be a viable option for nuclear power generation, because obviously uranium is a non-renewable resource. So if we were recycling it, rather than getting new uranium out of the ground every time, we would be able to, nuclear power would become more sustainable. So at the moment, nuclear power reactors that exist around the world are a class that we call Generation 3. And Generation 3 reactors can use some MOX fuel, but they can't use pure MOX fuel. They can use up to 50% MOX fuel in our current fleet of reactors. But there are a new generation of nuclear reactors that are currently being researched, Generation 4 reactors, and some of those are what are called fast reactors, which means that the neutrons are fast, they just have more energy, and that would mean that we can burn more of the uranium. So at the moment, the uranium-235 isotope of uranium is the main one that gets fissioned in a Generation 3 reactor, whereas in a Generation 4 reactor, more of the uranium-238, which is the predominant isotope in uranium, would also be able to be burnt, and the plutonium would be able to be burnt, so we could use MOX fuel, and also those minor actinides, the americium, curium, and neptunium, could also be burnt in Generation 4 reactors. So these don't exist on a large scale yet, but there are several Generation 4 reactors that have been built at an experimental or a demonstration scale, and this is a picture of one of them from Japan that's been built by the Japan Atomic Energy Agency. So if we go back to talking about the PUREX process again now, so as I mentioned, this tributyl phosphate ligand, which is used as the extractant molecule in PUREX, is a very good, it's very efficient, it achieves a good separation, and it's cheap and easy to make. It's also hydrolytically stable, so it doesn't degrade in the presence of acid, which is important because it is contacted with acid in the PUREX process. But it's not particularly radiolytically stable. So in the presence of a radiation field, it does tend to degrade. And as it degrades, it's no longer useful at performing that separation. So that is one downfall of the PUREX process. It means that over time we can't keep using the same organic solvent. It becomes degraded, and the organic solvent itself also becomes degraded by radiation over time, and it becomes contaminated, and it ends up being a secondary waste stream that needs to be dealt with. So one of the main disadvantages of solvent extraction as a technique for separation, particularly in nuclear context, is that in the process of treating one waste stream, we're generating a second waste stream in the form of that organic solvent and the organic ligand. So an alternative to liquid-liquid or solvent extraction for separation is to use solid phase materials to do the separation. And how this works is basically you have a solid phase material which you put in a column like this, and you have your solution of used nuclear fuel dissolved up in nitric acid with all the different colors being all the different elements. You flow that solution through your column, through the material. In this case, we've designed that material to be selective for the blue element. Let's say that's uranium. So all the other elements, the red and the green, flow straight through, but the blue element, the uranium, sticks to the solid phase material, and we end up with a solid that's been loaded with the element or the actinide that we've designed it for. And the advantage of this process is that we don't create a secondary waste stream, and because this, in theory, this solid phase material that's been loaded up with uranium can be directly converted into a fuel without creating a secondary waste. Is the grand idea. So what some of the challenges are when we're trying to design these solid phase materials to do actinide separations are that they need to be stable, both to acid and to radiation, and they need to be selective. They need to be able to remove only the element that we want them to, even though they're being exposed to a lot of different elements. Almost, half the periodic table of elements is in used nuclear fuel, and we want it to just pick out one or two elements. And we also want these materials to be porous because we want them to have high capacity for the element that we're separating out. So the higher the porosity, more surface area, more capacity. So the materials that I work on and that I'm going to be talking about for the rest of this presentation are they get their stability by being made from an inorganic framework. So usually either titanium dioxide or zirconium dioxide, both of which are known to be stable to acid and to radiation. So that's how we try to build stability into the material. And then to get the selectivity, we use organic molecules. Just like in the solvent extraction, they have an extractant molecule. So we use similar organic molecules to incorporate into the solid phase material in order to make them selective for the particular element that we're trying to separate out. So we end up with hybrid materials that have the inorganic part, which makes them stable, and the organic part, which makes them selective. So I'm going to go through a few examples now of some materials that I've made and how they've worked. So the first example that I'm going to talk about is functionalized titanium materials for selective uranium separation. So in this case, the titanium dioxide or titania is the inorganic framework. It's not a particularly complex framework in this case. It's not porous. It's just particles of titania, like this little circle here, and they've been coated in an organic ligand. In this case, that organic ligand is this one here, which has an amine group, because amines, this NH2 group, is known to have an affinity for uranium, because we were trying to make a material that was selective for uranium. So there are the results here. So basically how this experiment works is that we've taken our titania particles that are either coated in this amine ligand or not coated in this amine ligand, and we put them in contact with an acidic solution that contains a bunch of different elements. In this case, the elements that we tested were uranium and some fission products. So these are cerium, europium, and ytterbium, which are all lanthanides, which are fission products, and cesium and strontium, which are also fission products that are present in used nuclear fuel. And we can see that at pH 2 to 3, so reasonably acidic nitric acid conditions, even the titania that hasn't got that amine coating on the surface are taking up, or they're extracting 20 to 50% of the uranium, and none of these other elements are being extracted. So it's nice and selective. That's what we want. And if we put the amine ligand onto the surface of the titania, then we can increase the amount of the uranium that gets extracted to 30% at pH 2 or 90% at pH 3. And we're still seeing no extraction of any of those other fission product elements. The problem with this material, these functionalized titania particles, is that they have very low capacity. So we're only doing experiments with low concentrations of all of these elements in this case. So because the titania is not porous, it doesn't have a high surface area, we're not getting a high capacity for the element that we're trying to separate. So in this next example that I'm going to talk about, instead of talking about uranium separation, we're talking about a minor actinide-lanthanide separation. So I kind of alluded to this briefly when I was showing you the periodic table. This is a really difficult separation, and it's one that's really exciting, and there's a lot of research being done into it. So it's a necessary separation if we want to burn the minor actinides eventually as fuel at some point in the future when we have generation 4 reactors. And we need to separate the lanthanides from the minor actinides to do that, because the lanthanides actually really like absorbing neutrons. So if we have the lanthanides in there with the minor actinides, then the minor actinides will never see a neutron, they'll never fission, they'll never transmute into a stable element. They'll never fission and give us any energy. All the neutrons will get sucked up by the lanthanides that are in there and be kind of wasted. So we need to separate out the lanthanides in order to make use of the minor actinides. But it's really hard because the minor actinides and the lanthanides are almost identical chemically. They're the same size, they have the same charge, so they're really hard to separate from each other. And that's why there isn't any commercial or industrial separation technique for doing this minor actinide-lanthanide separation yet. There's lots of people doing research into it, including me. So to give you some context of where this minor actinide-lanthanide separation would fit into that idea of recycling used nuclear fuel. So we talked about PUREX being the first step, where we take used nuclear fuel and we separate out the uranium and the plutonium. And then what we're left with is, in our nitric acid solution, is the minor actinides and the lanthanides and all of the other fission products. So what we can then do with that solution is we can do what's called a group extraction and separate the minor actinides and the lanthanides together from all of the other fission products. And then we end up with a solution that just contains the minor actinides and the lanthanides. And we can focus on just achieving that more challenging separation. So there are, as I said, lots of people internationally researching this minor actinide-lanthanide separation. And a lot of people, in France in particular, are looking at solvent extraction as a method to do this separation rather than using solid phase materials. So these are the two extractant molecules that have been designed by other groups that are kind of state of the art at the moment in terms of being able to separate the minor actinides from the lanthanides. So these are more complicated molecules than the tributyl phosphate one we saw that was being used in PUREX, because it has to achieve a more difficult separation. So it's not surprising that the molecule has to be more complex in order to do that. But so this molecule here is called BT-fen, or bis-triazinyl phenanthaline. Don't worry too much about the name, but it is used in a process called SANEX, or selective actinide extraction. We have more exciting, innovative names here. And this molecule here, called DTPA, is used in ALSEP, which stands for actinide-lanthanide separation. So many interesting names. So basically, I've looked at this molecule in particular, the BTP one, and I've tweaked it a little bit to make it more easily incorporated into a solid phase material. But the structure is pretty similar in the hopes that a molecule that has a similar structure will be able to achieve that minor actinide-lanthanide separation once I incorporate it into a solid phase material. rather than using it in solvent extraction. So in this case, again, I'm using titanium dioxide or titania as my inorganic framework. But in this case, rather than just being particles, I've made these porous beads. So this is a lovely scanning electron microscope image of one of those beads. In real life, the size of them is about 2 millimeters in diameter, so they're very small, but we can look with the electron microscope at the internal structure of that bead and see that it has this beautiful porosity on the inside. So it's got a nice high surface area. We can get lots of our organic molecule in by coating all the internal surfaces as well as the external surface of these beads with the organic molecule. And then we can try to do our minor actinide-lanthanide separation. So we did the coating of the titania, both particles and those porous beads, with the same BTP-like molecule. And we see that when we coat the particles, we do get minor actinide-lanthanide separation. So this AMs is americium, which is a minor actinide, and this is europium, which is a lanthanide. And so we see extraction of the minor actinide, about 20%, and no extraction of the lanthanide. So we do get good separation, which is great, but yeah, the capacity is very low. We're only seeing 22% extraction of the americium. And it takes about 2 hours for that reaction to be complete. Whereas if we use the porous titania bead coated in this same BTP organic ligand, we double the amount of the minor actinide that we can extract, up to 44%. And we still see no significant extraction of the lanthanide. So that was a really promising result. And as well as that, having that more open porous structure made the reaction much faster. It took much less time for the reaction to reach equilibrium and for all of the minor actinide to be extracted, which is also an advantage. But we're still looking at only 40–45% extraction of the americium, right? So to try and make that even better, I changed the way that I made the material. So rather than making first an inorganic framework and then trying to coat the surface of that with the organic ligand, I did a different type of synthesis where it's a one-pot synthesis where you just put your inorganic precursor and your organic molecule in at the same time. You react them together and you end up with a precipitate or a powder that has a lot more of that organic ligand incorporated into the structure of the overall material. So in this case, rather than titanium dioxide as the inorganic frame part, I've used zirconium dioxide as the inorganic part. And again, this structure may look a little bit familiar. It's still very similar to that BTP structure that we know is able to achieve minor actinide-lanthanide separation. And in this case, I've just put some phosphate groups on the sides of that BTP moiety in order to coordinate with the zirconium. So the reaction, so we did this same americium-europium minor actinide-lanthanide separation. So when we have a 1:1 ratio of the minor actinide to the lanthanide, which is what was done in the previous slide that I showed you, we see 99% extraction of the americium and 94% extraction of the europium. So both of them are being significantly extracted, which tells us that this material has a good capacity for both, because it's extracting both the minor actinide and the lanthanide. And we do have some selectivity there. So even though you wouldn't use this kind of in a once through, because you'd still be extracting a lot of your europium, if you did this enough times, you would be able to effectively separate the minor actinide from the lanthanide in several steps. So we have what's called a selectivity factor of 7.4. But the really exciting thing with this work was actually that I also did the experiment when we had an excess of the lanthanide present and much less of the minor actinide present. So it's more difficult when there's 40 europium atoms for every americium atom for the material to only pick out the minor actinide element, which is what I've tried to kind of visualize in this picture here, where the purple is the lanthanide and the red is the minor actinide. And indeed, even when there is an excess of the lanthanide present, which is what it would be like in a real life situation of real used nuclear fuel, then we still saw selectivity for the minor actinide over the lanthanide with this material. And this is actually the first time that a solid phase material was shown to show selectivity for a minor actinide in the presence of excess lanthanide. So that was a really nice result. So as well as making these materials selective and high capacity, we also want them to be stable. So to finish up, I'm going to talk a little bit about work I've done into improving the stability of these kinds of solid phase separation materials. So in this case, I'm talking about material that would be used for this group extraction of the minor actinides and the lanthanides together. So again, it's a zirconium phosphonate, like the previous example I talked about, but it's a different phosphonate molecule. It's this one down here, which is not as complex and is not able to separate minor actinides from lanthanides, but it is able to selectively remove the minor actinides and lanthanides together from all of the other fission products. So if we just look at this plot, basically we see that, so originally when I made these materials, I made them at pH 4 using potassium hydroxide. So that is this blue one here called 4K. And we have quite good capacity or extraction of the lanthanides originally. But if we dry this material or heat it up to 150 degrees, or if we put it in contact with acid, it loses a lot of its capacity to absorb the lanthanide elements. So that was problematic. And we found that if we decrease the pH of the synthesis to 3, which is all of these other, the red, the green, and the purple were all done at pH 3, we significantly improve our thermal stability. These materials are still maintaining pretty good capacity after they've been heated up to 150 degrees. But they're still, the one made with potassium hydroxide and the one made with sodium hydroxide still have pretty poor acid stability. But if we use lithium hydroxide, then we have much higher acid stability as well in these materials. And the reason for that is that when we use lithium hydroxide, the reaction to form the zirconium phosphate material is slower. And that means you get more bonding between the zirconium atoms and these phosphate groups. And the more of those zirconium phosphate bonds you have, the more stable the material is. And that was a similar story when we looked at radiolytic stability as well. So in this case, the material was a mixture of both zirconium and titanium dioxide that's been functionalized with, we looked at 2 different ligands. So one organic molecule that just had 1 phosphate group and another one that had 3 phosphate groups. So there are more of those zirconium or titanium phosphate bonds when we have more phosphate groups in our organic molecule. And indeed, we see that when we irradiate both of these materials with gamma radiation, the molecule that only has 1 phosphate group is lost from the surface of the zirconia titania, whereas the molecule that has more phosphate bonds to the surface is more stable and able to withstand that radiation and remain attached to the surface in the presence of gamma radiation. So that's pretty much it from me. I'm just going to conclude by pointing out, summarizing that, so used nuclear fuel still contains a lot of elements, actinide elements like uranium, plutonium, and the minor actinides that have the potential to be recycled and used again as fuel. So if we think about reduce, reuse, recycle, the reuse part would be taking the uranium out, making it back into uranium oxide and using it again. The recycle part, I think the distinction there is that you're turning it into something different than what it was originally. So I think about that as being when we can make MOX fuel, so you can make fuel that is different to the original fuel by recovering the uranium and the plutonium from used nuclear fuel. And if we think about the reduced part, well, we can reduce the volume of the waste that needs to be stored and disposed. We can also reduce the radiotoxicity and the lifetime of what remains as waste and needs to be stored and disposed long term. And we end up with a more sustainable nuclear fuel cycle. And there are a lot of different ways to do these actinide separations. And I talked about solvent extraction, this liquid-liquid extraction is one method, as well as giving you lots of examples of solid phase materials being used to achieve these actinide separations, which is my particular favorite because it's what I do. I want to finish by acknowledging Science at the Local. Thank you so much, Kevin and Hamish, for inviting me to talk today. it's been a real pleasure, and yeah, it's been exciting, and it was an honor to be invited. So thank you. Thank you to my colleagues at ANSTO who have helped me with this work. A fair bit of the work that I've talked about today was done as part of my PhD at the University of Sydney with my supervisor, Professor Katrina Jolliffe, as well as our colleagues at the University of New South Wales and at CNE Argentina. So thank you to them. And thank you to everyone for logging in today. And please hit me with your questions.
Thank you, Jessica. Just a reminder again, the Q&A button is just at the bottom of your screen. We have 2 questions there already. If you can see those, Jessica.
I am looking. Oh, hang on. I'm looking at the chat rather than the Q&A. Here we go. So, yes, we have a question from Peter York. Do you agree with me that Australia should be using nuclear energy for electricity given its clean energy? Yeah, look, I have a bit of a mixed opinion personally about nuclear power. So I do think that at the moment, nuclear electricity is the cleanest type of electricity we have that can provide baseload power. And therefore, it's probably the best option that we've got at the moment. I think it would be great if we could get renewables to a point where they were able to provide baseload power, and that would be really exciting. But yeah, at the moment, nuclear is the cleanest energy that we have that is completely reliable and doesn't depend on the weather and the wind and the sun. And so, yeah, it's going to be, I think it is an important part to have as part of the mix. That's just me personally, by the way. Okay, and another question from Ned Blagojevich saying, Synrock was invented in Australia, ANSTO, and it's the world's best waste form. How does your work fit with this established product? Yeah, well, I think that you kind of pointed out the fact that Synrock is a lot further along its technology readiness journey. So it is already a technology that's been developed for a long time, and it's ready to be used, and it is a really really powerful waste form technology that is able to make sure that nuclear waste is kept in a really safe way, and is not going to release any of its radiotoxicity into the environment at any point down the track. So it's the best option for the open nuclear fuel cycle, right? So whereas I've been talking a lot today about the closed nuclear fuel cycle, and I haven't really talked about the advantages of the open fuel cycle, but there are, of course, pros and cons to both. There's less handling of the actual radioactive material in the case of an open fuel cycle. At the moment, it's much more economic. So yeah, I think it's important to keep research going in not just one direction, but to make sure that you have capability to maintain flexibility depending on the conditions that turn up in the future. Okay, Gideon Goosen. When you say cleanest energy, how much waste will still have to be disposed of? So I think when you're talking about when I said that nuclear power is the cleanest energy that we have that's baseload at the moment. So, well, okay, so how much waste will we still have to dispose of is not an easy question to answer, because nuclear power is used internationally in other countries, obviously, but they all treat their waste differently. So in case of France and Japan, they do reprocess their waste already using the PUREX process so they reprocess all the waste that comes from their nuclear power production. And so the volume of waste that they are left with after that would be reduced. But in other countries like the US, they have an open nuclear fuel cycle. So they would have larger volumes. I could not give you numbers off the top of my head, but I'm happy to take that question on notice and do some looking into it and talk to people who probably know more about the actual volumes of waste that are happening if need be. All right, so many questions, it's exciting. Could any of the nuclear waste be used to manufacture batteries needed to store renewable energy? Oh, that's an interesting question. I've seen that, I was reading recently some work about nuclear grade graphite that had been used in nuclear reactors being used for making batteries, I think, which was really cool. But I'm not familiar. I'm not aware of any work being done in using nuclear waste to manufacture batteries. But that doesn't mean that it doesn't exist, because there is a lot of work being done out there, and it's impossible to know everything about everything. So yeah, not sure about that one, sorry. But it's a cool idea. What is your opinion on thorium nuclear reactors and CANDU reactors? Oh, okay, yeah, getting technical. So thorium nuclear reactors, again, I will put my hand up and say I am definitely not an expert. So in reactor design, full stop sort of thing. I have colleagues who work in reactor materials, so particularly designing materials that can be used to build nuclear reactors that will be a lot more, that are, you know, have good mechanical stability and radiation tolerance, and in the case, if we're talking about molten salt reactions, then corrosion resistance and all the things that structural materials need to be. But that is not my area of expertise. But okay, thorium reactors,